flip-flop. Alternate the lighting of the LED. Make a schematic diagram here. I also have this PCB layout. Let's see. Actual circuit using two relays, flashing LED at the right side. So we got now this an alternating LED flasher. Provide an oscillator circuit or a clock or controlling any kind of circuit. The circuit diagram for making the transistor a stable multivibrator. I'm using also this. This is my header. These are my layouts. This is a it has a multiple uses. Hello everyone, welcome to my channel, and we have a new circuit here. Multivibrator.
Now, we're going to connect a jumper to our header. It becomes an LED flasher at the left side when you connect a jumper. So this NE555 timer can be used as an LED flasher. This is at the left side. How about the right side? This is an onboard LED flasher at the right side. Connecting the jumper settings, it becomes a flip-flop on alternate flashing of the LED. Can we connect an external LED here? Let us connect. Okay, let us first remove the onboard LED flasher and flip-flop. And we're going to use this, an external LED, to put it in here. This is now the output.
And we also have this another output. Let's connect this. This is a different connector. I'm using different header or connector. Put it on the right side. We got now this. For 555 timer flip-flop or from Astable multivibrator, and we can connect the onboard. This is the external output. Now we can now connect the onboard LED. So let us now see the circuit diagram of this NE555 timer to analyze the current flow and the design of the circuit. If you are interested, let's move on. So this is now the circuit diagram. We have the 9-volt supply or 12 volts also works, BCC. And then we have the 555 timer, the output LED. And then we have the resistor here connected at the pin 7 and 6 and 5, and then the capacitor, another capacitor, and the power on LED. And this is connected to the chassis grounded. That is the symbol for chassis grounded. And this is the circuit diagram of the Astable mode NE555 timer. And this is now the current flows once you power on the circuit. This is the state of the circuit. The arrow here corresponds to the direction of the current flow. There's a node here. So when you power on the circuit, we have here power on the circuit, LED power on. So it means that power LED is turning on. This one, that is the red one. That is the red one at the right side. And we got this KBL at VCC RD1 D1. So when you powering on the circuit, the power LED turns on. We get the first KBL on from VCC 9 volts, VCC minus the voltage drop at RD1, then D1 equals 0. Solving the value of the resistor here, or I mean the voltage drop of the RD1, we got VCC minus VD1 transposition, and we know the voltage supply 9 volts and the voltage rating of the LED 2 volts given in the data sheet of the LED. So we get 7 volts. We're trying to find the values of the resistor here to prevent the LED from burning. That's why we're going to solve for the value of resistor, and we got now the voltage drop of 7 volts. Applying a KBL. Using Ohm's law, voltage at RD1 is equal to current times the resistor of the RD1. Transposition, substitution, we know that 7 volts, and the current rating of LED to turn on is 0.02. Since we're designing a circuit or that will make this LED to turn on, that's why I'm using 0.02, and we got 350 ohms by calculation, but I'm using 330 ohms by available, or I'm using 470 ohms, but I still don't have this 330, so I use 470 ohms. So we got now first the value of this resistor, since we are going to compute for all the values of the resistor in the circuit. This is the first KBL, VCC, VRD1, VD1, and to the ground. Now let's come to the second. Here we have this KBL at VCC to pin A to pin 3, RD3, D3. Where is that? Pin 8, RD3, and then D3 into the ground. Now, at this state, capacitor is charging. So when you look at the arrow here, from the voltage supply, and then it goes to the pin number 8, and then goes out to the pin number 3, and then to RD3 and to the LED. The question here is, what is the configuration of the NE555 timer? Is it current sinking or current sourcing at this state? As you have seen here, this 555 timer is current sourcing. Look at the flow of the current here, the arrow entering into the pin 8. The 555 timer now is current sourcing because it gets its power to the positive supply, sourcing its power to the positive supply. So it is current sourcing, and it flows down to this RD3 resistor and to the D3 and to the ground. So this LED now, what is the configuration? This LED is current sinking. 555 timer is current sourcing. 555 is sourcing its power to the positive supply. LED is sinking power to the ground. Sinking current. Sourcing current for the 555 timer. Look at that. So that is the second KBL. That's why this portion is lighting. That is the first at this state. So we're going to compute for the resistor here, RD3, BCC, entering to the 8, minus RD3, minus the voltage drop at D3 to the ground. So we got here this one, the BCC. Since 555 is sourcing current, LED sinking current, from datasheet, 555 I source is 100 milliamps at 15 volts. So it is capable of sourcing current of 100 milliamps. It means this is now the supply voltage to the LED, and it is capable of handling 100 milliamps to this point up to the ground. Since we are only using LED here as the load, and this LED is only, it needs only 20 milliamps, and this 555 timer can handle 100 milliamps. It means it is capable of lighting the LED 100 milliamps. This is now a source of the LED, voltage source, and the output level is high output level. Means this is now the supply or the source of the LED. Source current coming from this is 100 milliamps capable, and we are only using 20 milliamps. So there is it is capable of lighting the LED 100 milliamps to 20 milliamps. We're only using 20 milliamps. So from here, said here that it's now the total current, 100 milliamps. So that is the total current from this terminal 3, the output pin of the 555 timer. Output high level logic 1. So it means that is, as I've said, it is high logic 1 or high level. It means this is active. It has becomes the power source of the LED. And in here, LED to turn on is 20 milliamps, so it is sufficient to turn on. So that's why it is sufficient to turn on the LED, because this as a power supply, it is capable of handling 100 milliamps, and it is capable of turning on the LED. It only needs 20 milliamps. So let us now solve the KBL at the BCC, RD3, BD3. BCC entering to the pin 8 to goes out to 3, RD3 and D3. It means that the supply here is 9 volts. We get here 9 volts. BCC, transposition, substitution, voltage drop at D3 is 2 volts. That is the data sheet of LED, 2 volts to turn on. And we got a voltage drop of 7 volts. That's a voltage drop here is 7 volts. And then using Ohm's law, voltage is equal to current times resistor. Transposition, RD3, since we're going to compute for the value of the resistor here to limit the current that flows into the LED. We know that 7 volts, and then that is also the current rating of LED to turn on, 0.02 ampere. So we get 350, but I use 470 ohms my available resistor. That is now the second KBL. 555 timer is sourcing current, and this LED load is sinking current. So at this state, as I've said, at this state, capacitor is charging through BCC, RA, RB, C1, output high. So that's why when the capacitor is charging, also the current flows into this node to the right, to RA, RB, C1. So capacitor C1 now is charging through RA, RB. And this is now the formula for computing the capacitor charging. So when the capacitor is charging, T1 is equal to 0.693 times the sum of RA plus RB times C1. The sum of the two times C1. That is the time or time period of the capacitor when the capacitor is charging. So as you have seen here, when the capacitor is charging, that makes the 55 timer to source current. So this part is sinking LED and the N555 timer is sourcing current. So current also flows here, charging the capacitor at this state. Pick the values of resistors, capacitor. In my design, I pick the values of RA, RB, and C1. That is arbitrary. And why did I pick that? In order to produce how to compute the time of to measure the time when the capacitor is charging. You can experiment or use any values of RA, RB, and C1 just to know the charging speed of the capacitor. Since I'm using RA 1 kilo ohms, RB 1 kilo ohms, C1 1000 microfarad 16 volts, 1 kilo ohms, 1 kilo ohms, 1000 microfarad 16. Using the formula for to measure the speed of the charging, 0.693, substitution 1K, 1K, 1000 microfarad plus 2 becomes 2 times 10 to the 10 cube. And then we have this microfarad times 10 to the negative 6. Also 2 times 10 cube is also 2000. 1000 times 10 to the negative 6. Okay. And then we get this by simplifying the microfarad, move it to the left, it becomes 0.001000. Moving this 1000 to the left by 6 times, 1, 2, 3, 4, 5, 6 becomes 0.001100. So the time or the time period when the capacitor is charging is 1.386 seconds. That is, they call it a time constant. Now, another one, where do the current flows? Also, current flows into the terminal number 4 or pin 4. This is a reset pin. You need to put it high in order not to reset the system because we're designing a stable mode multivibrator. So this one, pin number 4 should be connected to the positive supply, and this one is for voltage stabilizer voltage, C2. This is the control voltage for voltage stability or stabilizer. C2, which is 104, that is the commercial value of C2, which is equivalent to 100 nanofarad. So we know the speed, time constant or times constant to charge the capacitor at this state. So the current flows here into the power LED, to the pin number 8, to the pin number 3, and to the ground. Then also current flows into the pin number 4 and also into the pin number 5. That is the active line at this moment when this state capacitor is charging. So let us now the other state when the capacitor is discharging. This is now the behavior of the circuit when the capacitor is discharging. So let us now see the current flow here. So when you see here, our LED turns on still, but this time the other LED is on and the other LED is off. So let us now see what is this. 555 timer, sinking current, LED sourcing current, and capacitor discharging. So at this state, the 55 timer is sinking current. Why is it sinking current? At this state, capacitor is discharging. Okay, and also 55 timer is sinking current. So let us first see this, where the discharging of the capacitor, or else let us first discuss this. When the capacitor is discharging at this state, it discharges from C1 to this node, to the pin 2, also to the threshold, and then into the C1 RB, and then to the pin number 7, and then to the ground. They all coming out to the ground from this, entering into pin 2, entering into pin 6, pin 7, also pin 8 to the ground. We can compute for the time constant or the speed of the discharging of the capacitor. At this time, the output here is at a low level, 0 volts. Why? Because the capacitor is discharging. Since this is 0 volts, it means this line, the LED here, the other LED will turn on. That's why it is now turning on and off. Oh, what's wrong? Okay, this time the other LED turns on and the other one is not turning on because the output of this 555 timer is at a low level, 0 volts, because this capacitor is discharging. So it means this output now becomes the input of this LED, and this LED now is sourcing current, and this 555 timer is sinking current because it gets its power to the ground. See the connection, pin 1 to the ground, and the LED now is sourcing current, getting its power to the voltage supply. And now we can now have, this is now the formula for the discharging time constant discharging of the capacitor, 0.693 times RB times C1. See this? The discharging formula, C1 times RB. So means current flows into the C1, RB, into the pin number 7, and to the ground. Substitution, 1K, 1000 microfarad. Simplifying, and we got 0.693 seconds. That is the time constant, or the speed of the discharging speed of the capacitor. So we now know the speed of discharging of capacitor, and as we have seen here, LED sourcing current, 555 timer sinking current. So why is it sinking current? Because it gets its power to the ground. And this now is sourcing current, the LED, the load. That's why the other one is sinking, the other one is sourcing, the LED. So it blinks on and off. So let us now see the KBL at BCC. We're going to compute for the values of the RD2 to limit the current flow of the LED. BCC minus voltage drop, RD2, D2, and then entering into the 555 timer, 555 timer into the ground. So we got the first KVL into the table of the 555 timer. This 555 timer is capable of sinking current of 200 milliamps at 15 volts. Since we're using 9 volts, so we can approximate it to 200 milliamps or less than 200 milliamps. Capable of sinking 200 milliamps. So it means it is capable from this node to this node. It is capable of handling a current or sinking current to the ground of 200 milliamps. Since we are using only LED here as a load, which is 20 milliamps, so it's still this 555 timer capable of sinking current of 200 milliamps, very big compared to the sourcing current, I-sync. If LED is 20 milliampere, if this is capable of handling 200 milliamps, so 20 times 10 LEDs. If your power source is 15 volts, but in the table we got only 15 volts, 200 milliamps. There's no 9 volts in the data sheet, so still we can approximate it 200 milliamps. Current entering to the 555 capable of handling this 200 milliamps sinking. So we got now this, the BCC RD2 D2 into the ground, 555 to the ground. Transposition, substitution, same. The voltage rating of the LED to turn on, we got 7 volts. Ohm's law, using Ohm's law to compute for the value of RD2, B is equal to IR of the RD2. Transposition, substitution, the same. Current to turn on, 0.02, and we got 470. Available resistor. I'm using 470. So we got here 470. This one is 470 and this one is 470. Now, let us now see this. So this NE555 Astable is, they call it square wave oscillator because of the characteristic of turning on, turning off, on, off, on, off, square wave. And this is the waveform, square wave. We also have here the duty cycle or the on time. Duty cycle refers to the on time period when the, you can see here the on time of the LED, on, off, on, off. The on time here is has a formula D duty RB over RA plus 2 RB. That is the on time or the duty cycle percentage. 1000 ohms plus the substitution 2 RB. We got 3000, 1000. We got 33%, 1/3. So as you have seen here, the on time of the LED is 1/3 when it is on and 2/3 it is off. You have seen here the on time is lesser than the off time. It blinks. The period or the time of the off time is longer than the on time because the on time refers to the duty cycle is 33%. And we can also calculate the frequency of the oscillation. We're going to calculate the frequency of the oscillation, this oscillation, the frequency, by using this formula. Frequency is equal to 1 over time constant, or is equal to 1.44 divided by RA plus 2 RB, close quantity, all of parentheses C1. This is the formula. By substitution, we know all the values here, and simplifying, and we got 0.48 Hertz. Or you can check that frequency by using this formula. Since what is the time constant? The total time of the on and off of the LED can be used by using this formula. Total time constant is the time of the capacitor T1, capacitor when the capacitor is charging, plus the T2, capacitor is discharging, is equal to 1.386 plus 0.693. We computed that, remember? The T2 and the T1. So we got 2.079 seconds. Here, when you're using the formula, where is the total time period? You see that here? 2.0. See, we're using the formula for solving the frequency here. 1.44 over RA plus 2RB times C1 is also, you can use this formula, 1 over the time constant. 1 over the time constant of 2.079. 0.48 Hertz, the same as using the formula 144 RA to AB. We got the same frequency using different formula, 1 over tau or 1.44 RA plus 2 RBC1. That is now the frequency of the oscillation. So we got now here the total the diagram, complete values. Power LED 470, RA 1K, RB, C1 1000 microfarad 16 volts, C2 104. The connection, the pin connection, and then into the output. RD2, RD3 470. So you notice here that the output sometimes it becomes an input because of the characteristics of the charging and discharging of capacitor. When the capacitor is charging, it becomes an output. Current flows into the ground. The 555 is sourcing current. When the capacitor is discharging, it becomes an input. Current flows into the enters in terminal 3. So this capacitor serves as a switch to this terminal 3. This is now the the circuit diagram with actual values. It serves as clock generator, as we have seen here, or as we have seen, clock generator or oscillator. And I'm using this header, input, output, header, jumper. Header. This is my schematic using the header. And I also have here the layout. This is a layout. This is the actual layout of this circuit. As you have seen here, you see here. This is the output terminal, and then this is the input header. Then the 3 LED on board and the power on and the components. So that is the analysis of the current flows of the NE555 timer, a stable multivibrator, also known as transistor flip-flop. So thank you for watching the video. See you on my next video.